Hello, hello, welcome. Folks are signing in. Good to see you. All right, we don't want to lose our time here. It's a couple minutes after the hour. So, we're in our our quarterly kind of run here. We'll see how this goes. It does, keep us on the edge of our seat, ready for the next presentation, right? And for the next meeting together. So we're excited to have Robert. I'm going to let him introduce himself and just sort of take it away. We're going to do questions at the end. All right.
Great. Thank you so much, Rhonda. Yes, hello, everyone. I'm Robert Johansson from Stockholm, Sweden. And I will talk about artificial general intelligence from a CBS perspective. I'm an associate professor at Stockholm University. I have in psychology, but I have also conducted research in this domain for about 7 years. I can also mention that I'm from, I went to the psychologist program at Linköping University in 2005, which was only 2 years after the first ACT and RFT conference happened in the small city in Sweden, Linköping. So it was a lot of talk about RFT when I started training to a clinical psychologist. And before that, I had a background in computer science and AI. So it was very natural already then to think about, I wonder if it's possible to design an AI system from the perspective of RFT. That was then about 19 years ago. And this is still one of my main interests. In Stockholm, we have the Stockholm AGI lab, which the main 3 people is myself, Patrick Hammer, and Tony Lofthouse, who might be on the call. And the work we do with this particular AI is called Open NARS for applications, that I will talk more about. That is created by my 2 colleagues, Patrick and Tony. We are funded by Digital Futures in Stockholm. That is a collaboration between various universities. So I will briefly speak today about artificial general intelligence as a research topic and ask the question if RFT can be a theory that can guide research in this domain. I will speak about the particular system we use, the non-axiomatic reasoning system. I describe what I call machine psychology. That is the type of research we do, and show some empirical studies we have conducted, and also do some reflections related to the task force report. So artificial general intelligence, or AGI, it's really the task of creating general purpose system rather than specially trained systems like game playing or image recognition and stuff like that. And this was the original goal of AI, to create these general purpose systems. And it has been called the holy grail of AI research by Margaret Bowden, for example. And of course, this is an extremely difficult problem to create a system that is generally capable in many, many contexts. But since 2008, there is a distinct, let's call it, research field within the AI field about AGI, with a community, journal, and annual conferences and so on. So this work that I present is, let's call it, part of the AGI research. And the question everybody asks is then how to build a system like this and what inspiration to take. And many approaches are available, but a very popular version is trying to simulate the brain. Another popular version is trying to mimic human behavior as closely as possible as close as possible. So ChatGPT, for example, would be some kind of example of that. Another approach is trying to identify a single unifying principle and try to implement that. And for example, in the work by Pei Wang, he identifies the central principle of intelligence as adaptation with insufficient knowledge and resources. And this work that I present today is based on Pei Wang's NARS model. But the question then that basically I have worked with for the last 7 years is if RFT can be an AGI theory. So in the AGI field, it has been a call for more theory-driven research and several suggestions what constitutes a good AGI theory. And one suggestion is that such theory needs to be concrete, compact, and correct, compact, and concrete. So RFT is correct in the sense that it has lots of experimental research to back it up. It's very compact in the sense that it is minimalistic in the sense of Occam's razor. It's not concrete in the sense of that it can lead directly to an implementation. You can't take RFT and immediately program it into a computer. And to address that problem, how to make RFT concrete, me and my colleagues have used this NARS model, the non-axiomatic reasoning system, to provide a formalization of RFT. And just as an example of the compatibility between these theories is that we in contextual behavior science define learning as ontogenetic adaptation. And Pei Wang in his NARS model defines intelligence as adaptation with insufficient knowledge and resources. So NARS is called a principal AI in that it tries to implement a single principle. Maybe as we also think that conditioning is a kind of single principle that is used all the time. So it's a deep compatibility between RFT and NARS in this sense. And this was the thing that attracted me to NARS 7 years ago. So very briefly about this model. It's described in this book from 2013 by Pei Wang. And Pei Wang he has worked with this since the 1980s. He was the PhD student of Douglas Hofstadter, that some of you might know. And Pei Wang's student, Patrick Hammer, has together with Tony Lofthouse implemented this NARS model that we use, and he has worked with us at Stockholm University since 2021. So he's one of my two closest colleagues, so to speak. And Pei Wang has also visited us at Stockholm University several times. So the NARS model, the NARS system implements this logic that is described by Pei Wang. And it is a reasoning system, and which is designed to be adaptive. And the way it does that is its design is totally around this premise of operating with insufficient knowledge and resources. And that sets the agenda for the whole design, so to speak. The brilliant move by Pei Wang in the 1980s was to find a very unusual logic described by Aristotle a very long time ago called a term logic. And it's thanks to this very, very unusual design that it's possible to create this kind of system. And it is designed around a set of logic rules that are applied in every cycle that the system operates. So the reasoning process can stop there or go on forever, so to speak, as long as resources allow. And this last line sounds a bit strange, but the non-axiomatic reasoning process is a non-computational process, but implemented in a computer. So it is computation that are applied in constant time at every cycle, but it's repeated all the time and can be stopped anywhere. So the process in itself is non-computational. NARS has truth values, 2 of them that are called frequency and confidence, and these can be used to handle conflicting evidence, both positive and negative evidence, and revise based on that. And very importantly, compared to all the other AI out there, NARS is not pre-trained. This is so important. It's not pre-trained. It learns in interaction with the environment. The semantics is called experience grounded, and another way to say that is that a NARS system operates within its behavior stream. It's possible also to say that NARS is neither computation nor a dynamical system. It's more like a self-organizing process. So it's neither traditional symbolic AI, it's not machine learning. So what does it look then to interact with NARS? So this is, for example, if it runs on a robot. This is just one example of a robot picking up things. But let's say that we use a system like this to create a match to sample situation. And this is, I will now describe how it's possible to formally describe something perceived with vision, for example. So if this is the sample, we can also have other parts of the vision field and just call them anything, like left and right. And I call these rel and func because that's where we place the C rels and the C funcs. And this is just one way to describe a situation like this. Something green is to the left and something blue is to the right. And this thing indicates that it's a temporal event. So these are 2 temporal events just describing this situation. It's also possible to describe something like this. So 2 events can describe the same object in this sense. A red triangle is in the sample, a blue square is to the left, a green circle to the right. It's also possible to connect NARS with some kind of pre-trained network, like an image classifier, and to use this as part of the reasoning process. Like this. So the cat is in the sample and the bird is to the left. Or maybe it has different colors. So this, as I said, this is not the pre-trained on data. So you can just start the NARS system like this and provide some initial instructions that it has one operation that it can do with 2 parameters, for example, left and right. So if we provide a situation like this is like a learning procedure for NARS. We can say to the system G exclamation mark, which means that G is now a motivating event, which triggers the system. If it doesn't know anything, it will just do, let's call it motor babbling. So it just executes one of the operations. After that, we can provide a consequence as researchers. And based on that, the system can derive a contingency like this. So this is just something that the system learned from this single interaction. And let's say if we wait 100 time steps and the same situation occurs again, and G is once again a motivating event, the system can, based on the previous training, execute the same operation. This is now a decision making and not only motor babbling. All the experiments I present here or almost all of them, is not conducted manually like this. It's using a Python experimental framework, Open Sesame, and it's possible to connect with NARS with a Python interface. And NARS is not at all like commercial or anything. This is possible to download from GitHub. So it's free software. Machine psychology. So what I mean with machine psychology is a functional approach to the AGI problem. And I specifically mean an interdisciplinary approach combining functional psychology with NARS. And one analog is to say that machine psychology is to computer science what psychobiology is to biology. Meaning that with psychobiology, you can manipulate experience and some kind of, let's call it, biological factors. With machine psychology, it's possible to manipulate the experience of the system, but also the mechanisms. One way to summarize what I have done the last 7 years is to dissect Pei Wang's NARS system and turn it upside down. And I will explain what I mean with that. So basically, to use RFT and functional psychology as a guiding framework, it's needed to start somewhere else than the start of the system. So in my experiments, I start with just one part of Pei Wang's system, temporal induction. That is what he calls the 7th layer. That leads to classical conditioning. Procedural reasoning and goal deductions enables operant conditioning together with this thing. So these two enable operant conditioning. These two plus this thing enables non-arbitrary applicable. Let's call it animal level concrete relational reasoning. Adding a further layer enables what we call functional equivalence. And the last part, what we think enables arbitrarily applicable relational responding. So I will show some of this work now, starting with the first of these. I will demonstrate some of the abilities on all of these 5 levels. So classical conditioning. So from Pei Wang's book, we now use a system that only uses what he describes as NAL7, seeing reasoning on temporal events. So this is an example then that might look a bit primitive, but let's imagine that we present something blue, nothing happens. We wait 100 time cycles, and then we present something red and then something green. This leads to the system deriving, let's call it a prediction. Whenever I see red, I see green. So the system derives this prediction. Whatever is in boldface here is derivations. And this is derived using the, let's call it, mechanism of temporal induction. Then we later concurrently present red and blue. Then later again, we only present blue, exactly as we did before at the start of the experiment. But now an event is predicted, this event. So it's a function transfer in the classical conditioning sense. So this is something that can be done with an extremely minimalistic NAR system that only can do something close to classical conditioning. And with Jan de Houwer's way of talking about learning and classical conditioning, this is a change in behavior. From the start, blue predicted nothing, but it changed to blue predicting green. So it's a change in behavior due to pairings of stimuli, the blue and red stimuli. Okay, so operant conditioning. So this is reasoning on operations and goals as events in Pei-Wang system. I will show a few examples here. So once again, if we start the system, this is the only instruction to set up the system. And let's say that we want to train the system to always pick blue. And let's say that we design an experiment with this. And so basically, it will look something like this, that the first time we show the procedure and we establish G as motivating, the system will use, once again, motor babbling, since it doesn't know anything. We can provide a consequence, and then by the mechanisms of temporal induction, it can derive this contingency. So the same mechanism of induction is used for both classical and operant conditioning. However, and we can do the same with a left operation. However, if we then want to use this knowledge in the same situation later, the mechanism used to carry out the execution of this operation is called goal deduction. So it's the mechanism that enables the execution of that. So this is possible to illustrate with a learning procedure like this. If we don't give feedback, the system doesn't learn anything. During training, the system is more and more correct over trials. And then in the testing without feedback, it's 100% correct. This is another way what I have here. So instead of only this is how I typically like to illustrate these experiments, that the system gets more and more confident in its, let's call it, the hypothesis. So if the system derives this hypothesis of, for example, if blue is to the left, I should press left. This is an increase in the confidence value, one of the truth values that I mentioned. And this is a really nice way to track the learning of the system. This is another operant example. The same start. We want to train the system to always select green. But in the middle of the task, after we have trained the system to that, we change the contingencies. So instead, we reinforce the selection of blue. So this is something that NARS can learn. So it will at first quite quickly learn to pick green and demonstrate that without feedback. But if we change the contingency, it will initially be not correct at all, but adapt and relearn that. So it's possible then to see how the hypothesis of the green hypothesis goes up, and then down it gets punished, so to speak, in that. but the blue goes up instead. And this kind of adaptation, this is something that is extremely hard for something like reinforcement learning. How they are constructed is like designing a utility function that can be something else in the middle is very hard with those setups. So I would say NARS is more operant than reinforcement learning. It's also possible to learn like longer contingencies, like conditional discriminations, to learn something like this. Yeah, so you can only add more terms, so they become longer. So let's see. So summing up operant conditioning, it's enabled by the mechanisms of temporal induction and goal deduction. And it is possible in principle to remove one of these mechanisms, to manipulate if they are there or not, to demonstrate that they are necessary and sufficient for operant conditioning, for example. So moving to non-arbitrarily applicable relational responding. So this is something that is enabled by what Pei-Wang called variable terms or variable introduction. So it's abstraction abilities. And if we look at generalized identity matching, for example, this is an example of a paper we published at the AGI conference in 2022. And in this setup, so to speak, the setup is the same as before, but the training is, if we train the system on green colors and blue color, for example, whenever green is shown, pick green. Whenever blue is shown, pick blue. Then the test is, so to speak, if the system then is shown colors that it has never seen before, what will it pick? So it requires the system to act on the identity relation between colors. And NARS can derive something even more abstract like this, so to speak, by introducing variables. So if it learn these explicit continuances like green and blue, it can then derive something more general that it can use for other colors, so to speak. And this is also possible then to study using the same setup. And once again, this green line here describes the increase in truth value in the hypothesis. So the specific hypothesis is this one, and the general is this one. Last year, my colleagues developed some extension that they called comparative reasoning. And this can also be used, I would say, as a shortcut for general identity matching. So in this situation, if sample and left, for example, have identical colors, the system can, using this mechanism, derive a new relation that sample and left are equal in color. So then the system can learn that if something and something else are equal in color, I will match those two. So it's another way of describing the same situation as before. And it's also possible to use this for not only equal color, but for different colors or equal shape or different shapes. So the system can learn something like this with cues, same color or different color or same shape or different shape. It's also possible to use with other kind of concrete relations, like if something is more bright, for example, or less bright or larger in size. So the system can learn to pick, for example, something that is more bright. So, or less bright, or more size, or less size. So this layer of mechanisms is what enables non-arbitrary relations. And I think this is what Jan de Hauer would call effects of meta-regularities. And this, in the update of Pei Wang's book, he will include this. So it's basically the only extension that I know of that he has made for the last 10 years. Functional equivalence. This is something that Pei Wang calls statement level inference, or reasoning on statements as terms. And this, I would say, enables some kind of building blocks of language. So I will speak about these two things, how to derive functional classes, and then some experiment with the Sidman experiment. So let's say that the system is started with this. It can do two things, the say operation and the select operation. And then if we show something red to the left, and the system is trained to say red, the sound, and we reinforce that. Then at a later stage, we show the word red. OCR is as in, OCR detecting text. And use the same operation, saying red, as here. So this is an indication then to derive something between these two events based on that it was followed by the same operation and consequence. So this is valid in the logic to derive what Pei Wang calls an equivalence between these statements. And I think we could say in CBS language that we put them in the same functional equivalence class. But it's also possible then to derive, to introduce a variable to have a more abstract knowledge learned from that. So let's say that we have learned then that, okay, if we have seen a red word somewhere, it tends to be functionally equivalent to a red color. So let's say what we know that, and then we are trained in some other procedural task that if I see the red color, I do some other operation like pressing upwards. Then, okay, we reinforce that. The system will learn something like that. If we then present the same situation, but instead of the red color, we use the word red, and we use G exclamation mark to trigger the decision mechanism of the system. The system will then execute up, since it could substitute this event with this thing. It would also work with presenting the word red at another position, since the system learned a general select operation like this. So this is what at least what the sea lion people call the functional equivalence. And so to look at the very, very classic Sidman setup of learning probably many of you have seen it. When we hear the sound cat, we learn to pick the object cat. And when we see the object cat, we learn to say the word cat. And when we hear the sound cat, we pick the word cat. I probably said it wrong here. And then we would derive to say cat when we presented with the cat word and so on. I won't go into all the derivations here, but the trick used here is that if we have learned two of these four-term contingencies, like if the cat is the sound and the cat object is presented and left is picked, this is an identical contingency to this thing, except for that it's a word here instead of an object here. Once again, it's valid in the logic to derive something like this, that the conjunction of these two first events are equivalent. And since the very first of them are, once again, equal, it's possible to derive something like this, that the object and the word are now in the same functional equivalence class. And I think this is very similar to what Sean Hughes presented. He called it the effects of intersecting regularities. And what I presented in the first example here, this is already implemented in NARS, in OpenNARS for applications. This thing, to be able to pull out these things, it's not implemented yet. So it seems from this analysis that Sidman equivalence, so to speak, is possible to do with only this ability. And then moving up to arbitrarily applicable relational responding. This is using something that Peg 1 called relational terms. And what I show now is almost like a mixture between these. It's like the last thing there, acquired relation, is maybe what could be called a shorthand representation of that. And this is something that we're exploring the full extent of. But learning symmetry, for example. So if we are explicitly trained in picking y1 when x1 is shown, and picking picking x1 when y1 is shown. So we are trained explicitly in both ways. If we are then trained in a new situation, can we then solve the symmetrical version of that? So if we design an experiment with this, it's possible that the system learns the x to y relationship with feedback, learns the y to x experiment with feedback. Then we show these closer in time for the system to really derive the symmetry. Then we train the system in the A to B relation and test it without feedback on the B to A relationship. And how this works is that, so if the system are trained in both of these contingencies, so this thing is derived and this thing is derived, then the system can derive something like this. It's like a higher order substitution. Basically saying that if sample is x1 here, it's later to the left. So it's possible to describe this higher order substitution like this. So this is basically the mutual entailment in this situation, which can then be used to solve this particular situation. So if presented with a new situation like this, it can derive the B to A relation by using this abstract knowledge on the new situation, leading that it can solve this situation. So what I really like with this is that this abstract knowledge is also something that increases in confidence values. So it's really what Stephen Hayes described as these things, you know, are also operands in the sense that they develop over time, they are flexible, they are under antecedent control and under consequential control. So one additional thing that we played around with and suggested in a paper at the last year's, in a conceptual paper at last year's conference, is to use acquired relations. And acquired relations is this idea. Let's say that we act on a contingency like this. If x1 is sample and y1 is left, and I learn to press left, how about this? That when we act on a contingency like this, we derive a relation like this. And if a relation is derived like that, it's possible to describe something like this. This is quite wild, I think, to describe a functional equivalence between an acquired relation and a contingency. And then it can introduce variables with that thing, which leads that it can solve, it can develop mutual entailment if it learns the same thing. It can develop mutual entailment with a more, let's say, compressed representation. So it's possible to solve the same situation as before by deriving the reverse relation and then convert it back to the contingency representation. So this is really like moving between being the animal and the human being, so to speak. And to show something that is more advanced, I didn't say that, but this is just conceptual work. It's not implemented in open source for applications, and it's a very hard problem to implement it, to control all of it. So what I present now is just a sketch, and I will just briefly show it. Let's say that we train relations of same using direct experience, same, more, less. We can train a specific function of pressing hard, for example, or pressing light. We can learn the system that pressing more than medium is hard, for example, or pressing less than medium is light. We can also train the system that to substitute a green circle for more or a square for less and something like that, and then train some relational network using these symbols. And then having that network perform some kind of relational response. So this is just a sketch, but I think the take-home message is that the NARS logic seems to be able to describe all what we want with RFD. So briefly summing up here is that this is the research we have conducted that I call machine psychology. It's really like, it seems like these 5 layers of mechanisms seems necessary and sufficient for full RFT, so to speak. Of course, it's a lot to do before, like more advanced stuff, but it seems possible to describe most of it. So I will end with some reflections connected to the task force paper. Coherence across levels. I think NARS, it's really what attracted me from the start. It's very, very coherent with RFT and CBS. And it seems very compatible with evolutionary framework. NARS can open up for experimental research at very many different levels. It might be possible to conduct research that is not practical or ethical to conduct otherwise. I really like that NARS is one of the few systems, or the only I know, that has a behavioral stream, that operates within the behavioral stream. I think it would be possible to study the effect of specific treatment components with NARS, maybe like attention training, diffusion. It requires like a very experimental presentation of this. And maybe this is one way to look at it. This is Dermot and Yvonne's graph of an RFT network. If we can translate the clinical problem to RFT and we can translate RFT to NARS, then we can use NARS to model clinical phenomena with RFT. New ways to measure these things might be developed. For example, as I've shown, measure operands directly by tracking the changes in truth values. And of course, this is a transdisciplinary approach, combining AI and computer science in a coherent way with CBS. And I just want to mention that I think personally, this is what really means maybe the most to me, that the whole reason why we like CBS, I think, is because of how it looks at the purpose of science. And I think it could be extremely important to, when we develop AGI systems, to have this in the back of our minds. I think NARS can potentially collaborate with human beings, and maybe we could have something like human beings, systems like NARS, and systems like GPT collaborating. So in conclusion, I would say RFT has, for the last 7 years, proven to be exceptionally helpful for guiding AI research. It seems possible to formalize RFT with non-axiomatic logic. It seems possible to conduct experiment when NARS is the subject. I said that machine psychology is an analog to psychobiology, in that it's possible to manipulate both the experience of the system and its mechanisms. And maybe this technology have the potential to disrupt science in general, and of course RFT-based research in particular. So with that, I want to thank everyone for listening. Thank you very much. And I will stop sharing, and so I can see everyone.
Thank you for that. You've got some hand claps.
Thank you very much.
Yeah, we have about 9 minutes if people have questions, want to jump in and ask some clarifying, have any comments, jump on in. You don't have to raise your hand, you can just unmute and speak.
Could you help me understand what it means to apply motivation?
Did I say that?
I thought you said that you put together first a system and then you applied motivation.
I think I said that by using the instruction to the system G with an exclamation mark. So in NARS language, it's called that we establish G as a goal, but it's, I would say, equivalent to depriving someone of water, for example. Then water becomes motivating, a motivating event. That's probably what I said. So G exclamation mark is basically an establishing operation. If we as researchers write G exclamation mark, we are, so to speak, establishing that as what is called, we are conducting an establishing operation.
So it's a way of saying, if you will, you are now trying to achieve something.
Yeah, short answer, yes.
Thank you. Well, one more then. How is it that the second level, which is operant conditioning, was an 8, the prior one is a 7,
Mm-hmm.
and then the next one after an 8 is a 6?
Mm-hmm.
What should I derive from that?
Yeah, so it was my way of illustrating that my research process for the last 7 years has been, as I said, to dissect NARS and to turn it upside down. So in Pei Wang's system, he takes, maybe one can say, a more computer-based approach, that the simplest thing is what he called an inheritance, then it's something called similarity, blah, 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 blah. And then far up, he adds time to all of that. So he basically looks at having time to something is more complex than the other stuff. But I think you agree with me that from our perspective, we start with events in time and work upward from there. So the reason why I kept the numbers was to show both where to find it in his book, but also to demonstrate this turning around thing. Thanks for the question, by the way.
Thank you.
Yeah, thanks, Hank. Other folks that want us to jump in? I'd love to hear from some of the people that are just in in the trenches with the RFT work. That's that's what their sort of bread and butter, what they're doing, and what they think of this approach. If anybody's willing to jump in.
Any questions are welcome.
Everybody's very thoughtful, very contemplative. I'm using several sort of probably funny little analogies here, knee deep in the trenches and their bread and butter. But folks are out there doing wonderful RFT work, and I would love to hear if anyone can draw some lines between the stuff that Robert's doing and your work. I'd love to hear more.
Louise wrote in the chat. Thank you, Louise.
Mm-hmm.
I forgot actually to say NARS, I didn't demonstrate that, but NARS, as you saw, its way to describe operations at layer 8 is relations between the system itself and, let's call it, its operations. So the system actually has a self, and what the system calls a self is, I would say, similar to what we call the perspective. So if the system has carried out an operation left, and an operation up, and we ask the system, who are you? The system would say, I am someone who has carried out left and up. So its self-concepts is defined by its history of operations. But it also enables something like observing someone, like Rhonda opened the door and that led to G. So if I want to achieve G, I can then derive that if that happened for Rhonda, I can do it for me. And if we then also introduce variables, we can think of something like perspective taking. Oh, we have a new question for Yuki, from Yuki.
Thank you, Robert. Wonderful presentation, very inspiring. Just curious, because I have no experience or knowledge in computer language and psychology combined. How far are you in terms of training the machine computer in this learning? If we say, 0 is a baby level and 100 is adult, where are we at? And what do we need more to proceed to get to that adult level?
So question number 1 is that what I showed with mutual entailment, that's possible. It's just possible to download the NARS system that I showed. So one way to describe it is that the system is now stable at maybe a 16-month-year-old child level. I think you asked, why do we need more, or something like that?
What do we need more to mature this learning system? Or variables, stabilize the variables in the computer system?
So I'm not really sure how to answer the question, but so it's one thing to describe this with the logic, but it's another thing to, if you have a real-time system and events are coming all the time, how to prioritize between everything. It's a very, very hard control problem in that sense. And that's the hard task for the next years, I would say, when it comes to more advanced relational reasoning. Yeah.
Thank you. Very inspiring. Thank you. Looking forward to more coming from you. Thank you.
There's a comment from Nigel in the chat there too that maybe you could speak to really quickly. He says, great talk. It makes me curious about how you anticipate that NARS might leverage big data related to ecological momentary assessment or otherwise to tune it to any given individual's repertoire. So any thoughts about that?
So extremely quick answer. NARS is not good at all at, let's call it, big data things. What NARS could do is, this sounds very strange, but let's say that NARS has its own experience of something. I perceive this and this. Then it could then use that experience to recommend something to something else, to another person, for example. So that ability is not present in common AI system, to learn from its own experience and then you derive something from that. So Albert asks where to find resources. You can search for NARS online. There's something about that, and if you go to agicourse.org, I will paste the link. Then you can find a lot of resources there too. Pei Wang, when he visited Stockholm, he recorded a free course and put, by the way, all his books free online as part of that course.
Thank you, Robert. Thank you for coming and sharing your work with us. Thank you for the good discussion. I think a lot of people are sort of just marinating in it and thinking about just what's next in terms of the work you're doing and how we can learn more. So thank you.
Thank you very much, everyone. Thank you.
We'll see everybody in 3 months.
Yeah. See you. Bye-bye.